One point that I haven't mentioned is that when you draw the Frost diagram, you have to rotate the molecule so that there's a corner at the bottom. The Frost diagram only works if you have a corner at the bottom of the molecule. You can see that we have that here. There's a corner at the bottom of the molecule. But suppose that the molecule had originally been drawn like this. This is the same molecule as I have on the left. But you can't use this picture to draw the Frost diagram. This would give you the wrong answer. If you put an energy level at all the corners here, you would get this diagram. You would think that we have these two energy levels degenerate and these two energy levels degenerate as well. But again, remember, this is the wrong way of drawing it. Why is this wrong? Because we don't have the corner at the bottom. So if you, so let me erase these because again, that would be wrong. So if you're originally given a picture that does not have a corner at the bottom, well, don't panic. Just rotate the molecule until one of the corners is at the bottom, and then you can draw the Frost diagram. So again, the technique for the Frost diagram is that we draw one molecular orbital energy level at each of the corners, but we have to first rotate the molecule if necessary so that there's a corner at the bottom of the molecule. Also, I want to emphasize again that you only use these Frost diagrams for cyclic and completely conjugated molecules. If the molecule is not cyclic and completely conjugated, you can just use the normal methods for drawing molecular orbitals that we talked about a few minutes ago. We only need the Frost diagram for cyclic, completely conjugated molecules. But the rest of the molecules we're going to talk about today will be cyclic and completely conjugated, so we'll be using the Frost diagram for all of those. I'm not going to bother yet showing the pi electrons for this molecule. Before we talk any more about pi electrons, I just want to get a little bit more practice using Frost diagrams to show the energy levels. So we won't be counting electrons for a second, we'll just be showing the energy levels using the Frost diagram. Try drawing the pi molecular orbital energy levels for this molecule. I hope that the first thing that you did was rotate it until we have one of the corners at the bottom. So here, we have to rotate until the molecule looks like this. By the way, it could be any of the three corners at the bottom. It doesn't have to be the corner with the negative charge at the bottom. If you wanted to, you could have put one of these two corners at the bottom. The important thing is to have a corner at the bottom. Something I didn't mention before, but I guess you can see now, is that when I say you have to have a corner at the bottom, I mean that you have to have exactly one corner at the bottom. So this picture does not work, but even though there are some corners at the bottom, because there's two of them. So we never want to have a picture where we have two corners at the bottom. You have to rotate until you have only one corner at the bottom of your picture. All right, and now we can draw in our dashes. For each corner, we draw a dash. So we end up with 3 energy levels. Try to draw the pi energy levels for this molecule. Well, again, we're going to have to rotate the molecule because in this picture there's 2 corners at the bottom. Remember that we need to draw a picture where there's only 1 corner at the bottom. So we've rotated the molecule so there's only 1 corner at the bottom. And again, it can be any corner you want. You don't have to put the cation at the bottom. You could have put one of the corners with a double bond at the bottom. That would be fine too. And now at every corner, we draw a dash that represents a pi energy level. 1 dash at the bottom corner. Then these 2 dashes are both at the same level. And those 2 dashes are also at the same energy level. So this represents the pi energy levels for this molecule. Try to draw the pi energy levels for this molecule. Okay, so as usual, after I throw a question out there, I hope that you tried pausing the video to give that a shot. Well, we don't need to worry about rotating this molecule because there already is exactly one corner at the bottom, so there's no need to rotate the molecule. All we have to do is draw a dash at every corner. So that gives us 6 dashes. The bottom dash is by itself. These 2 dashes are degenerate. They're both at the same energy level. These 2 dashes also are at the same energy level, and then the top dash is by itself. It's the only orbital at that energy level. So this is what the energy levels look like for benzene. Please try to draw the energy levels, the pi energy levels for this molecule. This one was a trick question. You do not need a frost diagram. You should not use a frost diagram for this molecule. Remember that frost diagrams only apply to molecules that are cyclic and completely conjugated. Well, this molecule is cyclic, but it is not completely conjugated. We know it's not completely conjugated because this carbon is sp3. Since this carbon on the right is sp3, it does not have any p orbitals, so the molecule is not completely conjugated. When it's not completely conjugated, we don't use the frost diagram. We just use the old normal methods for drawing molecular orbitals. So how many p orbitals do we have here? 1, 2, 3, 4. Those 4 carbons all have p orbitals. So there should be 4 molecular orbitals, and since we're not using a frost diagram, each molecular orbital energy level is at its own level. Each molecular orbital is at its own level. 1, 2, 3, 4. Again, there's no need for the frost diagram because this is not completely conjugated. So in this case, there are no degenerate orbitals. All of the orbitals are at their own energy level. Okay, so I just wanted to throw that in to remind you that you only use frost diagrams when the molecule is both cyclic and completely conjugated. Otherwise, we just use the normal techniques that we talked about before. So far, when we've been drawing the frost diagrams, I haven't actually been putting the pi electrons in. We've just been showing the energy levels. Now we're going to start to consider what happens when we start putting the electrons in. What does the frost diagram look like? Well, in general, we know that every frost diagram has one energy level by itself at the bottom. Because remember, we're always going to rotate the molecule until there's a single corner at the bottom. Since we're always rotating until there's a single corner at the bottom, there's always going to be a single energy level at the bottom. And then on top of that, we're going to have pairs of energy levels. You've seen that in all the examples. If you look back at the examples that we've already done, you've seen that on top of the bottom energy level, we have pairs of degenerate energy levels. How many pairs? Well, that depends on how big the molecule is. So we can have a pair, another pair. We can have a bunch of different pairs. And that can go on basically indefinitely. And then possibly at the top, if there's a single corner at the top, we might possibly then have one last energy level that's by itself. It's also possible, if you look at some of the examples that we've done, that at the top of the molecule there's still just 2 corners. If the top of the molecule has 2 corners, then we could end up with 2 energy levels here. So we're not quite sure what the top of the diagram looks like. And again, these dots just indicate that we're going to have a bunch of these paired energy levels until we get to the top. And then the top is either going to be a final pair of energy levels or a single energy level by itself. Now, it turns out that for understanding Huckel's rule, we don't really need to worry about the very top of the diagram. Remember that we're pretty much almost never going to be putting electrons in the very top of the diagram because those are the highest energy and most anti-bonding levels. So we're just going to worry about the lower portion of the diagram down here. So the key point, again, about the lower portion of the diagram is that at the bottom there's always one orbital, that's the only orbital at this energy level, and then on top of that there's a bunch of pairs of molecular orbitals. And each pair has 2 orbitals at the same energy level. Now let's see what happens as we start adding pi electrons to the energy levels. where would we put the first two pi electrons? Well, here we put the first pi electron, and then we would put the second pi electron in that same low orbital. So this is what we would do if we have two pi electrons. And this should look fairly stable. We have a completely filled orbital down here, which is a fairly stable configuration. Now, let's see what happens if we take these two pi electrons and add another two pi electrons.